started here, we were talking about chapter 11. I think there was one last thing sort of in chapter 11, which in addition to electron configuration, was periodic trends we talked about. So we talked about some periodic trends. And when we look at the periodic table, as you go up and to the right and down, or up and to the right first, the atomic size decreases. And it will increase the atomic size as you go left and down on the periodic table. As you go up and to the right, the ionization energy increases. And as you go down and to the left, it decreases. A reminder that ionization energy is the energy needed to remove an electron from an atom. We also talked about electron affinity. Increases as you go up and to the right and decreases as you go down. Remember, electron affinity is actually the energy change that occurs when someone gains an electron, and those are typically your nonmetals. And that is not to be confused with electronegativity, which also increases as you go up and to the right and decreases as you go down. Remember, fluorine is really up higher on the periodic table. It's actually up here. But fluorine is the most electronegative element you could have. And electronegativity is the ability of an atom to bring electrons towards itself. I run right into that right there. So bring electrons towards itself. So electronegativity and electron affinity are different things. Electron affinity is basically what happens, the energy change that occurs when they gain an electron, but electronegativity is that ability of an atom to really draw electrons towards itself. All these periodic trends that we talked about all led to really what we know happens in the case of atoms, which is, I'm just going to start erasing things apparently. Let me get something to write with. There we go. As we go up and to the right on the periodic table, we have a much smaller size of the atom, which means electrons are held tighter. Even the outer electrons are going to be held tighter. We have things that take a lot of energy to try to remove electrons. And we have things that really have a strong affinity for electrons and like to bring electrons towards themselves. And that's why nonmetals, right, are guys that typically will gain electrons, right? As you go kind of the opposite direction, kind of down and to the left on the periodic table, you have things that are much larger, which means the outer electrons aren't going to be held as tightly. You don't have as high ionization energy, which means it doesn't take a lot of energy to remove those electrons. And you have things that are really not interested in bringing electrons towards themselves. They much rather get rid of their electrons. And that's why our metals, right, are typically the ones that will lose electrons. The most active nonmetal, right, is upper right of the periodic table. Most active metal is lower left of the periodic table, like we saw when we did the halogen experiment with the different layers, right? Fluorine more reactive than chlorine, chlorine more reactive than bromine. And as we saw in those videos of like calcium with water, you know, lithium and all those things that were they kind of threw the thing into water. As you go left and down, we saw much greater reactivity. I think we saw a video where we looked at lithium, sodium, and potassium in water. And obviously, potassium was much more reactive than, say, lithium. And again, that's because we're going down that group and more reactivity will increase. The other thing that we talked about again is, I think we mentioned it, but just in case, right? We have our core electrons, right? Which are actually these guys, core electrons, which are closer to the nucleus. And then in terms of bonding, we have our valence electrons, right? Which are the outermost, highest energy electrons, right? All right, any question on those periodic trends that we talked about there? All right, so that did wrap up chapter 11. Now off to 12, which kind of plays on what we just talked about. 12 was everybody's favorite chapter, which was bonding. Yes, let's draw some pictures and all that good stuff. So obviously, when we talk about bonding, there are only really the valence electrons that are involved, and those are the outermost electrons, the highest energy. And really, the easiest way to figure out the number of valence electrons is it is equal to the group number, right? So everybody in group 1 has 1 valence electron, 2, 3, 4, 5, 6, 7, and 8 valence electrons. So number of valence electrons equals the group number. You could also write the electron configuration if you wanted to, but this is obviously much, much faster. When we talk about bonding, there's really 2 types of bonding. There's sort of ionic bonding, which is between a metal and a non-metal. And based on those periodic trends, we know that what happens in this case is always the electron is going to go from the metal to the non-metal. The result of that is our metal will form a cation that's positively charged. Our non-metal will form an anion, which is negatively charged. And once again, it is that electrostatic attraction between those two that holds it together. There is no sharing of electrons here, right? No sharing of electrons. It is that positive negative attraction, also known as electrostatic attraction, that basically holds that together. And that is different than what we see when we get chemical bonding. No, when we get covalent bonding together. Covalent bonding is between basically 2 nonmetals. And because nonmetals are pretty much in the same part of the periodic table, they have very similar periodic trends, which means they are going to share electrons is basically what's going to happen. And what holds it together is that sharing of electrons. And as we talked about, the sharing can be equal sharing, which means you have a nonpolar bond. It could be unequal sharing, which means you have a polar bond. And what allows us to maybe determine whether or not something is going to be a polar bond or non-polar bond is we overwhelmingly use electronegativity to help us determine that. And if you remember, there's some electronegativity values that run from 0 to 4 on the periodic table. A guy by the name of Pauling came up with that. So I'll just draw everything higher here. So when we look at the electronegativity, again, values go from 0 to 4, 4 being the most electronegative and 0 being not so much. For example, our friend fluorine has a value of 4. Now, when we look at something like, say, hydrogen has a value of 2.1 and carbon has roughly a value of 2.5, we could calculate the change in electronegativity values by simply subtracting those numbers. Gives us a 0.4. And there were certain cutoffs where if you have a difference in electronegativity between 0 to 0.4, that's considered a nonpolar bond, which means you should expect equal sharing of electrons. If you're above 0.4, which is 0.5, I suppose, and below 2, that is a polar bond, which means that they're going to share those electrons unequally. It would go towards a guy that is more electronegative. And typically anything above 2 in most cases, not 100% of the time, will be ionic. And remember, you really don't need this one because you will know it's ionic as soon as you see a metal and non-metal. You don't need it. You know, you can basically do that. So in the case of carbon and hydrogen here, this would be a non-polar bond. We would expect the electrons to be shared equally in this particular case. Remember, if you get a difference in electronegativity, like if you did F2, that is 4 minus 4, that is 0. That is nonpolar and also sometimes considered pure covalent because it is a perfect sharing of electron situation. So they're sometimes referred to as pure covalent, but it's still a nonpolar bond in that particular case. You can show this in a polar bond like HF. What happens because of the unequal sharing of electrons between those two? Obviously, if you took 4 minus 2.1, that's a lot of math, but I think it's 1.9 you get there when you take that difference. That means that the fluorine is more electronegative, will gain a partially negative charge, and the hydrogen that is more positive will gain a partially positive charge. We could also represent that with a dipole arrow that we talked about that looks something like that, I hope. And it always points to the more negative side. The one that makes kind of like a positive side is the more positive guy in that bond, and this would be a polar bond. Remember, you don't always need electronegativity values to make a pretty good assumption if you are comparing two things that are in the same period. The guy that is further to the right will be more electronegative and will give you a polar bond. And if you're comparing two things in a group, the guy higher in the group will be more electronegative and it will give you a polar bond. So a lot of things that, especially if you're kind of comparing things that are in the same group or the same row on the periodic table, you really don't need the numbers. You can make a pretty good guess that it's going to be obviously a polar bond in that particular case. Any questions on that? Okay. So we talked about these sort of two types of bonding, and we talked about really representing these with Lewis structures and Lewis dot symbols. And when we use a Lewis dot symbol, and it's sometimes just generically called an electron dot symbol, we can basically use the element symbol and one dot basically to represent each of the valence electrons. Remember, there really is kind of no big rule on this other than typically we don't go more than 2 per side. And that is because that will max us out at 8, which is an important number, obviously, in bonding. So when we have like a ionic compound that we want to show Lewis structures for, we could take something like sodium, which has 1 valence electron. Again, 1s2, 2s2, 2p6, 3s1, plus say chlorine, which has 7 valence electrons because it is group 7. And chlorine there is 17, it looks like. So that's going to be a neon, 3s2, 3p5 here. And in this case, what's going to happen is this electron is going to transfer over here to our chlorine. The result of that is our sodium will now gain a positive charge, and our chlorine will accept that electron and gain a negative charge. When you're drawing compounds here that are ionic, you do need to include the charges to indicate that there's no sharing of electrons. And also, in a lot of cases, what we're looking at here is some brackets around maybe 1 or 2 of them. What happens, as we talked about, is this sodium loses this valence electron, leaves it with 10. It reaches neon's configuration, and the chlorine accepts that electron right there, which puts it into argon's configuration. And as we talked about, that is really the basis of all bonding, whether it be ionic bonding or covalent bonding, is for everybody basically to achieve the same electron configuration as a noble gas. They do not change into them, but in terms of electrons, they have the same number of electrons as the noble gases. That is what is referred to as being isoelectronic with each other. They have the same electron configurations. And the way it happens in ionic compounds is because of the difference in electronegativity, And those periodic trends, the metals will give up their electrons and they move backwards to the noble gas that came right before them. And what happens with our nonmetals is they'll accept those electrons and they will move forward to the noble gases that come after them. Any questions on that there? Remember, sometimes you need more than one of those guys, right, to have enough electrons for everybody to get to the right spot. We then talked about really kind of Lewis structures for covalent bonding. And when we draw Lewis structures for covalent bonding, remember there's a few important rules. One of the most important thing is counting up the total number of valence electrons in that particular molecule or ion. Remember that if it does have a charge, you need to adjust your count, basically, right? So you gotta, if it has a positive charge, you need to subtract that. And if it has a negative charge, you need to add to your total there in terms of electrons. Otherwise, you will be short when you go to draw it. Once you do that, you want the best arrangement, which means the least electronegative should be in the center atom. You will never find hydrogen or fluorine in the center. And that's because hydrogen follows the duet rule, which means it should only have 2 electrons total. So that means basically one line, it has to be on the outside, otherwise it will have too many electrons. And fluorine, which is the most electronegative, should never be in there because it's obviously will never be the least electronegative in that case. Once you have that, you want to do one single bond from the center guy to the outside atoms. And that's going to use up a total number of electrons. Whatever electrons you have left, go on the outside first in pairs until everybody has met the octet rule, right? Which is the important rule of bonding, which means everybody wants 8 electrons around it, basically. Any leftover electrons at that point go as pairs to the central atom. At that point, once you start putting electrons on the central atom, you should be out of electrons. You want to make sure everybody has met the octet rule. And it's at that point, if it has not met the octet rule, so if no octet met by somebody, you could try a double bond or a triple bond. Remember that you do not want to really double bond or triple bond right out of the gate. You want to kind of save that for any type of situation where it needs it. So if we had something like our friend NF3, nitrogen has 5 valence electrons, fluorine, there are 3 of them, it's group 7, that is 26 valence electrons. Here, nitrogen is less electronegative than fluorine. So we're going to put our nitrogen in the center, our fluorine around. We're going to do a single bond to each of them. That is 2, 4, 6 electrons. So we're going to put everybody on the outside, 2, 4, 6, 8, 10, 12, 14, 16, and we'll imagine there's 2 up there on top of it, which will be our 18. So that's a grand total of 24 electrons that have been put on here. We still have 2 more to go. So again, they should go on as pairs here on our central atom. We look at something like CO2, that's going to be group 4 there for carbon. 2 times 6 for the oxygen, that's 12, that's 16. Carbon should be in the middle, oxygen on the outside. Once again, a single bond, that's 2, 4, 6, 8, 10, 12, 14, 16. At that point, I've used up all my electrons, but my carbon is very much short. Remember that when we make a double bond, we're actually taking a pair of electrons in to do that. We're not adding more electrons. So that would then give us a double bond here to the carbon. And when we look at it, we are still short here. He's only got 6. In this case, we can make another double bond. If you couldn't, you would then want to move maybe to a triple bond in this situation. but we can, in this case, make a double bond. And you usually want to kind of use up all your double bond options before you move on to a triple bond. And in that case, we will end up with a double bonded oxygen on both sides, still only having 16 electrons, and everybody has 8 in this case. Any questions on that there? Now, we talked about as well, after we talked about drawing these things, we talked about the idea of molecular geometry and VESPER, which stands for valence shell electron pair repulsion model. And remember that when we do this for geometry, there's 2 really important things, and that is any double bond or triple bond counts as 1 electron pair and 1 bond. The other thing is if you draw a resonance structure, for example, if you drew carbonate, looks like this. You could draw a resonance structure by moving the double bond around, as we talked about. And these are resonance structures of each other. You could draw one more as well, move the double bond to the guy on the right. But if you draw a resonance structure, you can apply this geometry basically to any of them. They'll come out the same. Obviously, our third resonance structure here would look something like this, double bond over here to the right. So when you do geometry, the first type is pretty simple. When you have a diatomic molecule, the geometry is always linear because it's basically 2 atoms. So the only way to arrange 2 atoms is a straight line. That doesn't matter if it is like H2 single bonded, oxygen, which is double bonded, nitrogen, which is triple bonded. Doesn't matter if it's the same element or different elements. These would all be linear in terms of its geometry because there's basically only 2. So it doesn't really matter. It is when you get into really 3 or more atoms involved, the best thing to do is to always look at the central atom. And the 2 things that you really want to look at is how many electron pairs there are and how many bonds. And that will give you 2 types of geometry that we talked about, which is electron pair geometry and molecular geometry. So I think I have a table online and we kind of made a table, but basically it's always the central atom you want to look at. And it's the number of electron pairs. It is the number of bonds. And it will give you what is sometimes referred to as the electron pair geometry. It will also give you what is sometimes referred to as the molecular geometry or the shape. And, you know, there was some bond angle action going on there, I think, as well. So the first sort of situation that you could have is 2 electron pairs and 2 bonds. So something with 2 electron pairs is linear for the electron pair geometry. And it's also linear for the molecular geometry. It's got a bond angle of 180 degrees. That is a situation where you got something like this, basically. I'm just kind of straight across there. If you have 3 electron pairs and 3 bonds, 3 electron pairs, electron pair geometry is trigonal, planar. That's also sometimes referred to as triangular. The molecular geometry is also trigonal planar. It's got a bond angle about 120 degrees. That is something that looks like this here. It makes an equilateral triangle, basically. The next one that we talked about was 4 electron pairs and 4 bonds. So something with 4 electron pairs is tetrahedral for the electron pair geometry. Also tetrahedral for the molecular geometry. It's got a bond angle of 109.5 degrees. And that is something where you basically got something like this. Kind of makes a triangle on each side and a pyramidal type shape. Up until this point, as we talked about, the names on both sides here are the same. And that is because in each of these cases, when you draw your Lewis structure, there'll be no dots. So there's no non-bonding electrons. They're all bonding electrons. That means wherever those atoms end up is the same as sort of where the electrons end up, and the geometry of the molecule is basically the same. We only start to see different names when we introduce non-bonding electrons on the central atom. And that is because in terms of electrons, there is sort of a bad situation. The worst situation is when you have non-bonding electrons near non-bonding electrons. That's like dots near dots on your Lewis structure. The next worst situation is like non-bonding and bonding, so dots and lines. The best situation is this situation here, bonding and bonding. They can try to get away from each other as best as possible. But when we start introducing the non-bonding electrons, it's missing an extra atom, which allows everybody to actually get away from each other a little bit more than they can when there's an atom there. And because of that, what changes is the molecular geometry name is the only name that changes. The electron pair geometry name stays the same. So we talked about, I think, 3 electron pairs and 2 bonds here. And 3 electron pairs would still be trigonal planar. But because of the non-bonding electrons, this is our angular guy here. And it's less than 120. So for example, I think we looked at this guy here. I'll just draw the dots on the central atom. Something like SO2 is an example of that. It has, just looking at the central atom, 1 electron pair, 2 electron pairs, 3 electron pairs, and it has only 2 bonds. Obviously, this guy would have some electrons as well. Put them in. The next one that we talked about, I think, was 4 electron pairs and 3 bonds. So 4 electron pairs still going to be tetrahedral. But because of that non-bonding electron pair, we end up with something that is known as trigonal pyramid. Again, not planar, but pyramid. And this is less than 109.5 degrees. And this is something like ammonia. It makes this sort of pyramidal type of shape that occurs in that situation. And lastly, this was the last geometry I think you guys had, 4 electron pairs and 2 bonds. Again, 4 electron pairs in terms of the electron pair geometry will be tetrahedral. This will be bent or V-shaped. Also less than 109.5. Water is an example of that. Has that bent or V-shaped type of situation. Best way, as we talked about, I think when we were doing it, is kind of memorize the table. And again, count electron pairs is probably the best way to do it, and number of bonds. Any questions on that? What's that? They do want you to know it. So for us, I don't know. It'll be okay, I think, but you should probably know it as you continue on. Yeah. So I'd say roughly have it. Who knows? Maybe it'll show up there. I'm not sure yet, because I haven't written the final at this point. Any questions? All right, so we got the geometry here. We also talked about molecular polarity. So molecular polarity is different than bond polarity that we talked about a second ago with the electronegativity difference. Molecular polarity deals with the molecule as a whole. Is it going to be polar or non-polar? And we sort of boiled it down to kind of an easy way to just quickly identify if something is going to be polar or non-polar. First off, if it's diatomic molecules, it's pretty simple. Because there is, for example, only 1 bond in this entire molecule, but whether it be the same thing or different things, if you could ID what type of bond you're dealing with in terms of the electronegativity values, you'll know what type of molecule it is. So this obviously would give us a 0 in terms of electronegativity values, which means that's really a nonpolar bond. And because that's the only bond there, this molecule would also be nonpolar. And this one, based on electronegativity values, would be a polar bond. And once again, because that's the only bond in the whole entire thing, this guy would also be a polar molecule, where again, we could draw the dipole moment. And in this case, this could be referred to as the dipole moment arrow. Basically, it's going to be more negative towards the fluorine than the hydrogen. When you get to 3 or more atoms, you got to look at 2 things. You have to look at, are there polar bonds? And obviously, if the answer is no, there are no polar bonds, then your answer is it's a nonpolar molecule. And the second thing you need to look at is the molecular geometry, or the shape. So if you have something that it has an unsymmetrical geometry, that basically means when you draw your Lewis structures, there will be dots on the central atom. And for you guys, that's going to be your angular, that's going to be your trigonal pyramid. That's going to be your bent or V-shaped. If you draw anything that has any of those geometries and you have dots and everything is the same atom on the outside, it's a pretty safe bet that that's going to be a polar molecule. So that's pretty much all you have to look for. Dots, everybody's the same. Polar molecule, move on with your day. You'll be good. For symmetrical geometries, those are guys where there are really no dots on the central atom. So for us, that would be trigonal planar and tetrahedral. Again, the molecular geometry we're talking about here. And if all the outside atoms are the same, it will be nonpolar because they will cancel each other out. Remember, though, that this is the one that if you still have something with no dots, but all the outside atoms are not the same, it will then go from nonpolar to polar. So the opposite of that is not all same outside atoms. It will then become polar in that case. So that is sort of the difference. So, you know, if we had this guy here, that is symmetrical. Everybody's the same on the outside. It's going to be nonpolar. If you swap out one of those fluorines for a hydrogen, and now we'll become polar. Yeah. So that's what we're talking about there. And then that really only leaves linear, which means for linear, it's pretty easy to sort of figure out. Linear could be either CO2 is an example of that. It is a polar bond heading towards each oxygen, but because it's a linear molecule, they basically cancel each other out. So this guy would be a nonpolar molecule. But you could have a linear situation where they're all sort of heading in the same direction, the dipoles, and that would then become a polar molecule. So that's sort of the really quick way to do it. If you have your Lewis structure drawn correctly, basically no dots, everything the same, nonpolar. No dots, everything on the outside not the same, polar. Dots on your central atom, everything on the outside the same, polar. And again, that's a super kind of quick way to figure out molecular polarity. Any questions on bonding? A lot of stuff in that chapter. Huh? All right. So I think that is pretty much everything we talked about. The next chapter was everybody's second favorite chapter, maybe. It was nomenclature, back to chapter 5. Everybody loves naming, right? So chapter 5 was all about naming, and we talked about naming all kinds of things. So let's just run through them to make sure. I know you're professionals, but we'll do it anyway. So we talked about type 1 compounds, which is ionic, and that is a metal and non-metal. And as we talked about, it is always the metal that's most important when it's involved. And this metal is a group 1 metal. Group 2, group 3 are its silver, zinc, or cadmium. And what they all have in common is they have fixed positive charges. So that means that all you need to recognize, and you're going to use the whole name of the metal. And remember that the non-metal pretty much gets the IDE at the end of it. So obviously that's something like NaCl, that would be sodium chloride. Type 2 is also ionic, which also means, again, we have a metal and a non-metal together. And once again here, it is the metal that is most important. And that's going to be a transition metal. Or again, just to the right, under the staircase, or lead and tin and all those guys are, they have a variable positive charge. That means that when we name these guys, we have to add an additional thing, which is the whole name of the metal. We need a Roman numeral. And remember that the Roman numeral is not how many metals you have. It is the positive charge on one of those metals. And the non-metal will still get the IDE treatment at the end. The good news on these, as we've talked about, is you will always know the charge of what it's attached to. So in this case, FeCl2, we know Cl is group number 2, which means that's -1 each. That's a -2. There's only one iron, which has to be +2 to balance it out. Whenever you have anything that is charged, positive and negative, and you put it together, it needs to equal 0, the formula, right? When you put it together, the simplest way to get 0, in this case, would be 2. That means this name would be iron Roman numeral 2 because of the positive 2 charge on the metal. And regardless of how many of the non-metals you have, you do not use prefixes. So this is iron Roman numeral 2 chloride, not dichloride, unless you would like a line across it. Yeah, so do not use prefixes here. There is a place for prefixes, and it is not here. So non-metal, metal, pretty much type 1, type 2, they're pretty much named the same. It's just whether or not you need a Roman numeral or not. Any questions on that there? So speaking of prefixes, that is where we use type 3 situation. And type 3 is basically 2 nonmetals together. And here we do use prefixes. So that is our mono, that is our di, that is our tri, that is our tetra for 4. That's our penta for 5, our hexa for 6, our hepta for 7, our octa for 8, our nona for 9, our deca for 10. A couple of rules about these prefixes. We do not use mono on the first name. It is okay on the second name, right? The other thing that commonly happens is prefix to first letter of the element. We get a couple of vowels that back up to each other. So like a couple of O's or an A and an O, we typically get rid of the vowel off of the prefix when we do it. These guys are the simplest to name. You basically use the prefix if necessary and the whole name of the first element. For the second one, you use the prefix, and it's the normal non-metal with the IDE at the end of it. So like an NO2, that is nitrogen dioxide. Yeah. N2O5, that is dinitrogen. Penta, drop the A because the next guy is an O, so pentoxide would be the way to name those guys. Any question on that there? Now, hydrogen, which is really a non-metal, is really named more like a type 1 compound. So if you did have something like HCl, we think of this more like the acid version, H plus and Cl minus. So this would be hydrogen chloride here, especially if this was a gas, for example. So if it is hydrogen sort of there, even though it really is non-metal, they're sharing electrons, we sort of think of it and name it more like a type 1 compound. There's also things that have common names, right? Like H2O that is water. Make sure you put that right next week. Don't put all the favorite answers. All right, so that's type 1, that's type 2. We also have every other favorite thing. I'll spit that out maybe. Which is our polyatomic ions, right? And our polyatomic ions are groups of nonmetals that are together. We got like NO3 minus, like NO2 minus, that's like nitrate, that's nitrite. SO4 2 minus, SO3 2 minus, that is sulfate. Sulfite, sometimes we may put like CO3 2 minus is carbonate. HCO3 minus is hydrogen. Carbonate, or bicarbonate is sometimes referred to. There's also groups of 4 that are related to each other, like ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. This has the least number of oxygens, which typically are the guys that end in "ite," and the ones with more oxygens end in "ate." And that's what we see here: 8 for 3, "ite" for 2, 8 for 4, "ite" for 2. This is perchlorate, as we add the per in front of it because it has the most oxygen in a group of 4. This guy here is chlorate. Next to it is chlorite. And this last guy here is hypochlorite. Good way to remember it, as we talked about, is frankly, some people will remember all of the 8s and know that if you need an ite, you just take off an oxygen, everything else is the same. Or vice versa, learn all the ites, and if you need an 8, just add an oxygen. So that's a good way to remember it. Because a vast majority of our polyatomic ions end in 8 are ite, but there are some that end in IDE, like OH minus is hydroxide, which obviously ends in IDE. CN minus is cyanide, which ends in IDE. But because most of them are negative, really the only positive one you usually will come across is NH4 plus, which is the ammonium, not ammonia, but the ammonium ion, not to be confused with NH3, which is ammonia. But because most of the polyatomic ions are negatively charged, they pretty much will hook up with a metal. So a lot of these do follow kind of like type 1 and type 2 situation, which means you just need to look at the metal. So if you had NaNO3, that is sodium, which is group 1, and that is nitrate. So that would be sodium nitrate. If you had FeNO3 2, remember that when you have more than one polyatomic ion, you do need to put parentheses around it and how many that you have. This is a type 2 metal, which means we need to figure out the iron. Nitrate is -1, and there are 2 of them, so that's a -2. This means that this would be +2. So this would be iron Roman numeral 2 because of the charge. And once again, even though you have multiples of this, no prefix here. So that is just nitrate. You just use the whole name of the polyatomic ion in this case. Any questions on polyatomic ions? Yeah. So we finished out our wonderful conversation on naming with acids and how to name acids. And acids, always the cation for acids is H plus. So that's really what makes something an acid, is that ability, as we talked about, basically to produce H plus. So acids, in terms of naming, really revolves around oxygen. And it's all about our friend oxygen. And if the answer is there is no oxygen involved, are in the formula. The acid is hydro something ic acid, like HCl. That is no oxygen. So that would be hydrochloric acid. The negative guy is the missing part of that name. HBr would be hydrobromic acid. Now, if it does have oxygen, it will contain one of those polyatomic ions, most likely. And if it does have oxygen and your polyatomic ion ends in 8, then it is something ic acid, like HNO3. NO3 is nitrate, as we just talked about. So this would be nitric acid. No hydro there. H2SO4. I need 2 hydrogens because sulfate is -2 to balance out the charge. And because that's really sulfate here, that is going to be sulfuric acid. Now, if your polyatomic ion has oxygen and it ends in ite, it's going to be something OUS acid, like HNO2. NO2 is nitrite. This would become nitrous acid. What makes something an acid? And typically when you write the formula, you put the aqueous symbol next to them. That's how you usually know that it is an acid. Because otherwise, if we had HCl like we just talked about a second ago, and it's a gas, we would call it hydrogen chloride. But HCl with the aqueous symbol next to it indicates that it's in solution. That makes it an acid. It's able to release its H+, and we would call it hydrochloric acid. Any questions on acids or how to name things in general? Yeah. All right, so that was chapter 5. We took exam 2, then came back and went to chapter 8 after that. And in chapter 8, I think we started talking about some things here. All right, so chapter 8 opened up our eyes to our atomic mass, which again is the number that we see on the bottom of the periodic table. Remember that the atomic mass that we actually see up there is what is referred to as the average atomic mass of all the naturally occurring isotopes for that particular element. And there's actually a formula that we talked about as to how you calculate that. The atomic mass is basically the percent abundance of the first isotope times the atomic mass of the first isotope. Then we add it to the percent abundance of the next isotope times the atomic mass of the second isotope. And however many naturally occurring isotopes you do, you kind of call it and follow that pattern. That is essentially how they get those numbers that are on the bottom of the periodic table. We could also use this for a conversion, although we don't use it very much. If we looked at, say, something like sodium, it's like 2299. You could use that as 2299 AMU per atom as sort of the units. AMU is atomic mass unit. More often, though, we use this bottom number as the molar mass, right? And the molar mass has units of grams per mole. And that would mean that there are 22.99 grams per mole is the molar mass of sodium. We could also use it as a conversion factor in dimensional analysis, 2299 grams over a mole, or a mole is over 22.99 grams. If we have something where we're adding parts together, we just add up all the parts from the periodic table, 2 times 1.008 grams per mole, plus 16 for our oxygen, gives us a molar mass for water of 18.02 grams per mole, which you could also use, obviously, as a conversion factor. Molar mass is really important. It is really our conversion factor that we use to go from grams to moles. our moles back to grams. That is basically what you use. You go to the periodic table, you calculate the molar mass, and you use it as a conversion factor going in both directions. The other thing that we talked about was our friend Avogadro's number there, and Avogadro's number is what we use to go between moles and atoms, right? And that's really what a mole represents, is Avogadro's number, right? 1 mole of any substance is Avogadro's number. So 1 mole of anything is equal to 6.022 times 10 to the 23. Remember, the units here can change. It could be atoms, it could be molecules, it really could be anything. And that's obviously Avogadro's number. And we really do use it as a conversion factor. We could say that there are 6.022 times 10 to the 23 atoms per mole, or a mole is 6.022 times 10 to the 23 atoms, or they could be molecules as well. This is what we use again to go from moles to either atoms or molecules. Also remember, as we talked about, you should not use it unless it does mention something about that. You're given a number in mole, or given a number in atoms or molecules, or you need to solve something for atoms or molecules. Also remember that when you see MOL, that is moles, not molecules, right? So don't get those guys confused. This led us into obviously some calculations of grams to moles, moles to grams, and numbers as well. Remember that if we say had 4.5 moles of C2H5, and we were interested maybe in just the hydrogen, right? I mean, moles of this, the hydrogen. We could use the actual formula as a conversion factor. And in that particular formula, there would be 2 moles of carbon for every 1 mole of the entire thing. And there would be 5 moles of hydrogen for every 1 mole of the entire thing. So that's a way, as we talked about, sometimes you may be interested in just one of the elements, not the entire compound, but you could do a kind of stoichiometry sort of conversion and just say we were interested in hydrogen, which would be 5 moles of hydrogen in this case. Then obviously, whatever you get there, 22.5, I think. So sometimes we can use the actual formula itself to go from the whole thing to the individual things, as the bottom numbers sometimes referred to as the moles of each of that. And that led us into really talking about in this chapter 2 types of formulas that we commonly come across. And those types of formulas are empirical formulas and molecular formulas. So let's talk a little bit about those guys. So empirical formulas and molecular formulas. Empirical formulas is the simplest whole number ratio of what is present. Molecular formula tells us exactly how much of each atom or element is present. So if you had C4H10 as your molecular formula, that is something that you could reduce down by 2 in this case. The empirical formula would be C2H5 in this case. So you obviously need whole numbers for those guys on the bottom. They cannot be decimals, so you can't have like a half atom or anything like that. So it does have to be that. That's why some cases the molecular formula, which is like H2O, is also the empirical formula as well. For all ionic compounds, because we put it together in the simplest way to equal 0, when you take a positive ion and a negative ion. All ionic compounds are empirical formulas because they should be the simplest way to put it together to get to 0. So all those ionic compounds, metals and non-metals, should always be basically your empirical formulas. So that's just a simple way. Obviously, you could go from molecular formula to empirical formula. We also talked about how to calculate both of these if we're given some information, and very commonly we're given the percent composition by mass. are asked to calculate that. So if we did have something like water and we wanted to know the percentage of each of those to find the percent of hydrogen, we would take the mass of hydrogen that is present, which would be our 2 times our 1.008 divided by the molar mass of the entire compound, and we would times it by 100%. To find the percentage of oxygen, I won't do the answer here, but we would do the same thing, 16 grams per mole, which is the mass of the oxygen, divided by the mass of the entire compound and times 100%. When we get those values here and here, they should add up to about 100%, right? Because that is 100% of the compound. And very commonly, we're sometimes given the percentages of each of these elements, and we're asked what is like the empirical formula, what is the molecular formula, sort of based off of that. So there are several steps that we follow to calculate something like the empirical formula. And to get to the empirical formula, if we are given the percentages, we could assume 100 grams, because basically what that does is obviously convert the percentages into the same numbers. Once you have that, basically the next thing you want to do is take the grams to moles, and you're going to use the molar mass from the periodic table to do that. You will now have moles of all your elements. We'll call it mole A and mole B. You will take and divide by the smallest number of moles. So for example, if we had, again, say 6 moles of B and 2 moles of A, we would divide each of these by 2, which would give us 3 moles of B and 1 mole of A. And if we do that and we hit we hit whole numbers, basically are really, really close to whole numbers, like a 1.99 or something like that. This would give us our empirical formula. So in this case, it would be AB3. Now, if we were to divide and we didn't get whole numbers, so let's just say, for example, we did that step and we got 2.5 moles of B for 1 mole of A. That would give us an empirical form of AB 2.5. And again, you can't have sort of decimals there. So you do need to figure out a factor to multiply that number by to get to a whole number. And again, if you took 2.5 and times it by 2, that would give you 5. Now, the key here is you want to multiply by 2, not 5. And you want to multiply everybody here by 2. And that would give us A2B5 as our proper empirical formula. So convert to grams, grams to moles, divide by the smallest. If you hit all whole numbers or close enough to round, you're good to go. That's your empirical formula. If you don't hit whole numbers, you got to find a factor to do that. Again, not close enough to round. Endings like 0.33, 0.50, 0.25, those type of things are too far to round. You got to kind of figure out a number to multiply it by. Now, once you've got your empirical formula, if you want the molecular formula, you basically need 3 things. You need the empirical formula, which may be given to you or you have to calculate. You need the molar mass of your empirical formula, which you would probably have to calculate. And the last thing you need is the approximate molar mass of your compound. That number is typically given to you in the problem. So somewhere in the problem, they'll say, hey, the molar mass of this compound is whatever, 160 some odd grams per mole. So what you do is you take the molar mass of the compound that's usually provided to you. You divide it by the molar mass of your empirical formula, and that's going to give you a number. This is the one place where rounding is okay. You should round to the nearest whole number. Most of the times you don't have to. And that number is what you would multiply your empirical formula by. So you would multiply your empirical formula by this number. So let's just say we did this and the number was 2. We would take our empirical formula, we'll take this guy, and we would multiply by 2, which would give us a molecular formula of A2B6. Any questions on empirical formulas, molecular formulas? I would calculate them. All right. Then we rolled into really next kind of 2 chapters that kind of go together, which is chapters 6 and 7. And chapter 6 was really just an intro to balancing equations. So obviously we had reactants on the left-hand side of the arrow. We had our products on the right-hand side of the arrow. And it's always important to make sure that you have a balanced equation. So you had something like N2H2 NH3. A good way to approach it is to make like a little table. You could have your reactant side, your product side, your nitrogen and hydrogen. Left-hand side, there's 2. Right-hand side, there's 1. Left-hand side, there's 2. Right-hand side, there's 3. So a lot of times this table will help you kind of figure out where to start. Kind of the easiest thing sometimes is good. So in this case, we could put a 2 over here for our nitrogen, gives us 2. We then also multiply it to everybody behind, which would be 6. We now know we need to come over here and put a 3. So we still have 2. And again, 3 times 2 is 6. So this would represent obviously our balanced equation. Remember, sometimes you may need to use a fraction to balance an equation, which you can, but you do have to clear the fraction. So when you have balanced the equation, it needs to be all whole numbers for the coefficients. And by the way, that's the only thing that you should change when you're balancing an equation is the numbers that come in front. And they need to be the simplest set of whole numbers. So again, if you did something where you had 2a plus 2b gave you 4c, you could divide everybody by 2 here, and the properly balanced equation should be this one here, because you could reduce everybody down. Other things to watch out for that we've talked about in terms of balancing is obviously if you had something like, if you had something like this, maybe. This 2 obviously gets distributed into each of those things. So there would be 2 nitrogens, 6 oxygens, and 1 iron. Also, if you put a number in front, it also gets distributed to everybody. So that would be 2 irons, right? That would be 2 times 2. 2 times 1 is 2 nitrogens, times 2 is 4 nitrogens. 2 times 3 is 6 hydrogens, 6 oxygens. 6 times 2 is 12 oxygens there. So it's important when you're counting up everything, right, to make sure that you count correctly. The other thing that's kind of easy when you go to balance an equation is if you have an equation that has a lot of polyatomic ions on both sides, it's sometimes much easier to keep those guys together, kind of balance them as units rather than go kind of element by element. And you just go, okay, I got like 2 nitrates on this side and 1 on this side. I'm going to put a 2 in front of it. And then usually wherever you put that first number, what the second thing in that formula is where you go next to fix, and eventually it'll all sort of fall into place. So clearly we always want balanced equations, and that really led into, I think, chapter 7, where we talked about different types of reactions, I believe. And that is what was going on here, I think. So in chapter 7 really was types of reactions and ways to classify them. And remember that ultimately, as we talked about, pretty much you could classify the same reaction in many different ways, but ultimately all reactions pretty much fall under 2 big categories. And those categories are double displacement reactions and redox reactions. And there's really 3 reasons why a reaction takes place. The 3 reasons why a reaction takes place is the formation of a solid, the formation of water, and lastly, an electron being transferred. Those are really the 3 reasons why reactions take place. Underneath double displacement, which is basically when you have two ionic compounds together, they will switch partners. So the positive guys will go find the other guys, and it will make two new ionic compounds when they do that. And the result of this reaction is one of those guys that are made could be a solid. And that would mean if a solid is formed, that is a precipitation reaction, is what is more specifically called. What determines whether or not a solid will form is our solubility rules, right? Like nitrate is soluble in everything. Bromide, chloride, bromide, chloride, iodides are soluble in everything except for silver, lead, and mercury. So there are some exceptions along the way. So the solubility rules help us determine whether or not when we put two ions together, will we get a solid or not. The other thing that could happen is perhaps water could develop into one of these guys. And if water is formed, that is usually a result of an acid-base reaction. And sometimes an acid-base neutralization reaction. And that is basically when you take an acid plus a base, you get a salt and water is formed. Water always comes from the H plus from the acid, OH minus from the base is where we get our water. The salt is an ionic compound, and that's basically the two ions that are left over as a result of that. And those are really the two things double displacements take care of: the formation of a solid and the formation of water. Redox reactions are when you gain and lose electrons. So remember that if you lose electrons, you are being oxidized. And if you gain electrons, you are being reduced. That's like the oil rig. Our Leo the lion goes grr. Oxidizing is losing, reducing is gaining. Loss of electrons, oxidation, gain of electrons, reduction. You can find out if something is being oxidized or reduced by using a very simple number line, and positive to the right of zero, negative to the left. And if you look at really what's referred to as the oxidation state, but you can kind of think of it as a charge of something from the left-hand side to the right-hand side of the arrow. If something becomes more positive as it does that, that is becoming oxidized. And if you look at the charge and it's becoming more negative, that is when something becomes reduced. So under the redox sort of umbrella pretty much falls all the other types of reactions. So under redox, we have things like our synthesis reaction, our combination, and that is when basically two things make one thing. We also have the opposite of that, which is a decomposition reaction, where basically one thing becomes two things, right? We have a single replacement reaction, where one thing that has no charge comes in and replaces something that is an ionic compound. So if this was a metal, for example, it would come in and kick out the positive guy. At that point, it will actually gain a charge and make a new ionic compound, and that guy will come out with no charge. So an example, like we've done a number of experiments, take some zinc metal plus some hydrochloric acid. That's a positive, negative thing. This guy has no charge. The zinc will come in and kick out the hydrogen. The result of that is hydrogen gas is formed, plus some zinc chloride. And maybe do some balancing, like I'm a chemistry person here. When we look at this side, hydrogen has no charge. This has a +2 charge. This has a -1 charge. So in terms of being oxidized, to figure it out, we look at our number line. We look at zinc. Zinc started at 0, ended at +2. And the other side, it is becoming more positive. It is being oxidized. If you look at the hydrogen, hydrogen started at +1, ended at 0, going towards the more negative side. Hydrogen is being reduced in this case. Chloride is -1, and on this side it is -1. Nothing's happening with the chloride. It is a spectator ion. That's basically what it is. Speaking of spectator ions in terms of double displacement reactions, but we'll get there in just a second. One last one that goes here is combustion reaction. And a combustion reaction, really, most of the time people think of the organic combustion, which is something that has carbon, hydrogen, or oxygen plus O2 makes CO2 plus water. Remember, though, that the basic definition of combustion is basically there just has to be O2 on the left-hand side of the arrow, and technically it's a combustion reaction. So those are all the ones that fall under the redox umbrella. And to finish up here, the last main thing that we talked about in this chapter had to do with those double displacement reactions, which were the three different types of equations that you could write. And for example, if we had something like silver nitrate plus some sodium chloride, make some silver chloride plus some sodium nitrate here. This is the molecular equation. And remember that things that are strong electrolytes will 100% break apart in solution, conduct electricity really well, light bulb will go off. Things that are weak electrolytes will stay together, still be able to break apart a little bit and conduct electricity a little bit. And things that are non-electrolytes will dissolve, but really will stay together, not conduct electricity because there's no ions. But because silver nitrate is a strong electrolyte, we could break it apart into a silver ion and a nitrate ion. Sodium chloride, also a strong electrolyte, will break apart into a sodium ion and a chloride ion. Silver chloride, which is a solid, will stay together. Anything that's a solid, a liquid, a weak electrolyte stays together, or a gas. And sodium nitrate is a strong electrolyte, which means it will break apart. And this equation is sometimes referred to as the total ionic equation, or complete ionic equation. And in this equation, we can find our spectator ions, which are the guys that really are not doing anything but balancing out charges. They are not basically forming the product. These guys here would be our spectator ions. They are just watching. And that means that we can cancel these guys out, leaving us the third type of reaction that we talked about, which is our silver plus our chloride is coming together to make silver chloride. And this is known as the net ionic equation. And that's the equation that basically tells us exactly what's happening in this reaction. And when you write a complete ionic or total ionic equation, you need the charges, right? Otherwise, it will be incorrect because they are ions. You should always show the charges on that. Any questions on that there? All right, I think we will wrap it up there.